In this example, we're told that a 350 gram piece of copper at 420 degrees Celsius, that's our hot temperature there, it's placed in a 200 gram aluminum cup containing 1,000 grams of water at 23 degrees Celsius. That's our cold temperature there. We want to know what will be the final temperature. I'm not going to draw a picture, but I will come over here and draw a little temperature scale. I know the cold temperature is 23, and that's in degrees Celsius, and the hot temperature is 420. So the iron starts off here, or the copper starts up here at 420 degrees Celsius and cools down, and the water and the aluminum both start here at 23 degrees Celsius and warm up. And the final temperature, we know without any doubt, is going to be somewhere in between the 23 and the 420. So I'll just draw TF right there. I don't know exactly where it is, but I know it's going to be somewhere in there. In other words, the copper cools down this much, and the aluminum cup and the water in it warm up that much. And we'll use those differences in temperature when we set up the problem. And here's the setup. The heat lost by the copper has to equal the heat gained by the water plus the heat gained by the aluminum. The heat gained by the water plus the heat gained by the aluminum. And each of those will be an MC delta T. So let's write this out. The heat lost by the copper is MC delta T for the copper. That equals the heat gained by the water, which is MC delta T for the water, plus the heat gained by the aluminum, which is MC delta T for the aluminum. Now, if you want to, you can start just by writing that down. You don't have to write this down, but you do have to understand it. You have to understand that this is the law of conservation of energy applied to this specific situation. Now let's put in the numbers. MC delta T for the copper. Well, the mass of the copper is 350 grams. So 350 times the C for copper, which is 0.093, times the delta T for the copper. And we see over here the copper cools off that much. It's 420 minus TF. Okay, that's going to equal, I'm going to go down to another line because I can see that I'm going to run out of room there. That equals MC delta T for the water. The mass of the water is 1,000 grams. The C, the specific heat for the water, is 1, and the water warms up this much. You can see that's TF minus 23 plus MC delta T for the aluminum. The aluminum also warms up that much. The mass of the aluminum, we're given that as 200 grams. The C, specific heat for the aluminum is 0.22, and the delta T for the aluminum, just as the water, is TF minus 23. So now we're going to work out the numbers in this equation right here. Okay, the left side first. 350 times 0.093 times 420 comes out to 13,671. Then we have this minus, and we have to distribute 350 times 0.093 times TF. So that comes out to be minus 32.55 TF when we do the math right there. That equals, this part's fairly easy, 1,000 TF minus 1,000 times 23. So that's 1,000 TF minus 23,000. And then we have plus 200 times 0.22 times TF minus 200 times 0.22 times 23. And that comes out to plus 44 TF minus 1012. And then when we work all this out, if we add 32.55 TF to each side, then on the right we have 1000 TF plus 44 TF plus the 32.55. And that gives us on the right hand side of our equation, it gives us 1076.55 TF, just working out the algebra here. And then on the left side, if we add here, if we add 23,000 and 1012 to each side, then on the left we have our 13,671 plus 23,000 plus 1012, and we end up with 37,683. And then we divide and we end up with our final temperature, and it comes out to 35 degrees Celsius. And that's our answer. So there is a good bit of algebra in here, but it's fairly routine algebra. You should be able to do it. You should understand that the law of conservation of energy applied to this situation gives us a setup for the problem, something like this, and then we work out the algebra to get an answer. In this case, 35 degrees Celsius.